What actually are particles? Where do they come from? Short answer, they come out of fields. But how? What even are fields? And can we explain this somehow intuitively? Hi, I'm a physicist and this is how I wished I'd learned quantum fields. This is a fixed version of a video I made a month ago. Here I corrected a mistake and added more clarity and extra info to this super complicated topic. So, what actually is a particle? You probably know that particles are not like particles. But what do physicists mean when they use the word particle? We describe everything we measure related to particles using quantum physics. But quantum mechanics alone is not enough, as we'll see. That's why this is our current model of the particles that, together with gravity, make up our universe. This model is a quantum field theory, so it's quantum mechanics applied to fields. A theory that takes fields and quantizes them. We will understand what that means later. But now, what are particles according to quantum field theory? Within the framework of quantum field theory, particles are vibrations or excitations of fundamental fields. But what does that mean? What does a vibration have to do with a particle? And how are particles like that supposed to do anything? To understand all this, let's first get a feeling for fields. And then we'll see how quantum fields make particles, and why it's okay to call them that way. As we talk about how they interact, we'll even get a glimpse into how you can work with them. So, what are fields? We start with the simplest physics example I could think of, this. This is a temperature map, which you can also call a temperature field. Why is this a field? Because it has a value at every point in space. At every point you can measure the temperature. And that's the simplest kind of field. A value, a number at every point in space. These numbers can change and they can influence other things. For example, what is considered appropriate clothing. So a field is a mathematical way of describing something that fills all of space. It can be related to something real or physical in the sense that you can measure a number, like temperature. And even though this number may be zero in some places, it can, in principle, be measured anywhere. So, there's a thing that sits at each point in space. But for a general field, this thing doesn't have to be a number. It can be a vector, so basically a number with a direction, or a more complicated mathematical object. We'll see an example at the end of this video. So, in general, if there is a mathematical object at each point in space, we call the whole collection of objects a field. It's just more catchy than saying a collection of mathematical objects that continuously fill all of space. But yeah, this is basically a field. Now you might say, okay, but a temperature field is not that interesting. I mean, I want to understand where particles come from. And you're right, the temperature field is just an emergent field. It only exists because of the underlying movement of trillions of atoms. But the fields you probably have in mind are associated directly to fundamental interactions. So, let's talk about Newtonian gravity, which we can also describe with a field. You can characterize this field with the gravitational acceleration. So the thing that sits at each point in space is the gravitational acceleration. On the one hand, this is a number that tells us how strong the pull of gravity is. So, similar to the temperature map, we can picture the gravitational field around the Earth like this. Here more purple means stronger field. And stronger field just means that the gravitational acceleration has a higher value. But you know that the gravitational acceleration also has a direction. It points towards Earth. So, this is now a vector field, which we could picture like this. Similar to the classical electromagnetic field, which is also a vector field. Here, the electric and the magnetic field vectors tell us the field strength and its direction. But there's a crucial difference between them. The gravitational field is a static field, which means the values don't change over time. They only change if you, for example, move the Earth. The classical electromagnetic field, on the other hand, is a dynamic field. It can change with time. You can say the electromagnetic field consists of two parts. An electric field and a magnetic field. A changing electric field causes a changing magnetic field and vice versa. And this way the field can carry energy. Say you want to send a signal to your alien friend. So you set up an antenna and send out a strong electromagnetic signal. This basically means you send electrons through your antenna, which change the electric field around the antenna. This changing electric field then changes the magnetic field around your antenna, which then again changes the electric field further out, which then again changes the magnetic field, and so on. So you basically create a changing field. This changing is just a vibration in the field. This vibration then keeps spreading because a changing electric field induces a changing magnetic field and so on. This way the vibration transports energy through the field. So, you send out an electromagnetic signal to contact your alien friend. But your jealous Earth friend sees that and immediately vaporizes the antenna. Well, you don't care. The energy is already out there and it will keep going. Newtonian gravity tells us that if you remove the sun, the Earth will immediately leave its orbit. The effects of the field just vanish. So there the field is more of a mathematical tool. But electromagnetism tells us that even if the sun disappeared, we would still receive the light it had already emitted. So, the electromagnetic field is indeed something. It's a physical quantity. You can also say the field is a property of space. It's not just a tool we use to describe how antennas communicate. No, the field is actually doing something between the antennas. If this video is doing something for you, please leave me a like or a hype. Thanks a lot, I really appreciate it. So, the field is doing something. Its values change as it transports energy. It vibrates. And this vibration is what we call photons. Which brings us to quantum fields and how they make particles. Okay, we have seen how an antenna sends out a bunch of photons, which means it gets the electromagnetic field vibrating. But hold on. What does a vibration have to do with a particle or a bunch of particles? We'll figure this out as we elevate our fields to quantum fields. This elevation is what physicists call quantization. This may sound fancy, but it basically means that we adjust our mathematical model. Quantization tells us how we have to change our mathematical formulation to go from classical fields to quantum fields. Which, by the way, can be done in different ways, as we'll see later. Importantly, we went from a static field that is just there because of a source to a dynamic field that can keep vibrating. Now, quantization takes us one step further, to a dynamic field that can just start vibrating on its own, if it somehow has enough energy. In quantum field theory, we are dealing with fundamental fields that are similar to the fields we had before, but these fields don't need an external source to start vibrating. If the field somehow gets enough energy, it can just start. This energy can, for example, come from particle collisions or from heat. This vibration corresponds to a change in the field, not to a physical medium going up and down. In the temperature fields, if the temperatures are going up and down, that's a vibration. But there's nothing shaking in space. We give this change or this energy traveling through the field a name and call it excitation or vibration. This vibration has a frequency that tells us how fast it's changing. Now, this is what makes a quantum field quantum-like. The frequency is directly related to the energy put into the field. So, for a field to vibrate at a certain frequency, it cannot take any random amount of energy. It takes chunks of energy. If a field takes the smallest possible amount of energy corresponding to a certain frequency, the resulting vibration is a single particle. If the field takes twice as much energy, you get two particles, and so on. So we kinda get energy levels. You may know energy levels from atoms. For a hydrogen atom, an atom with only one electron, an energy level means a specific allowed energy for that single electron. Here it's a bit different. For a field, an energy level corresponds to the number of particles in that field. In an atom, the energy is quantized. In a field, the energy per frequency is quantized. For a given frequency, you have energy levels, but the frequency itself is continuous. For a massive particle, the frequency is related to the mass of the particle and its momentum. And the momentum or the speed of a free massive particle can change continuously. By the way, that's why you need a lot of energy to create a really heavy particle, because the smallest chunk of energy is already quite big. So, when you give a quantum field more energy than a single frequency unit, the field does one of two things, or a combination of them. It either stays on that frequency but goes to a higher energy level, so you get more particles, as already mentioned, or it goes to a higher frequency. In that case, you get a faster or a more energetic particle. Okay, so one particle corresponds to one package of energy, and we can actually count how many particles we have. That's why calling it particle makes some sense. One particle is the smallest chunk of excitation in a field. A field can not only create its own particles, it can also destroy them. We'll see how that happens later. While creating or annihilating particles, the field must respect things like conservation of energy, momentum, or charge. It must respect those things because it must obey certain symmetries. I'm not gonna get into this here, but this has important consequences for the particles. For example, it restricts the mathematical objects that fields are composed of. So it influences the mathematical behavior of particles. And that's why we have particles with those specific spins. Those are the only kind of particles that let the fields respect those symmetries. Okay, now you might say, so we have particles, but do they actually do anything? Well, one field can only produce one type of particle and its antiparticle. To make things interesting, we need more than one field. And that brings us to how particles interact. But first, I want to say thanks for all your questions and comments, and again, special thanks for pointing that out to me. Please let me know what you think about me putting out a corrected version of this video. So, you can assign a field to each fundamental particle, or actually the other way around. To get an idea of how they interact, we must first distinguish between force fields and matter fields, so-called bosonic fields, fields that produce bosons, and fermionic fields, fields that produce fermions, the particles that make up matter. The electromagnetic field, or photon field as we call it in quantum field theory, is a bosonic field. It corresponds to a fundamental force. Due to the mathematical properties of bosonic fields, bosons have integer spin, and they can stack on top of each other. The vibrations within a bosonic field can pile up. That's why you can have a bunch of photons. These photons can vibrate in sync and form a wave which you can measure. Fermions like electrons or quarks, on the other hand, cannot stack on top of each other. That's how they make up matter. If they could pile on top of each other, everything would just collapse. So, in quantum field theory, we work with an electron field, which produces or destroys electrons. And these electrons never sit on top of each other. But how can they interact? They can interact through the photon field. Before we get into that, I'd like to briefly mention you can't measure the electron field the same way you measure an electromagnetic field, where you can measure the oscillation of a bunch of photons. And the mathematical formulation does not require this. Actually, quite the opposite. Remember, we change the mathematical formulation as we quantize the fields. The most common method to do this is called canonical quantization. There you replace the fields with operators. Simply put, an operator is like a function. You know you can't measure a function, you can only measure the value of a function at a certain point. Similarly, you can't measure the operator. You can only measure what you get when an operator acts on a state. If you want to know more about this, please let me know. But if we can't even measure operators directly, why do we think that quantum field theory, an absurdly vast monstrosity, is a good description of reality? We think this is a good description of reality because it makes good predictions. That's how science works. You model something, and to verify it, you test the model's predictions against reality. Side note, the standard model is the current quantum field theory we use to describe reality. But even though it's pretty successful, it is probably not the final answer. But back to interactions within the standard model. Both fields, the electron and the photon field, continuously fill all of space. So electrons are basically passing through the photon field. That's why an electron could give some energy to the photon field at any time. In other words, it emits a photon. Now another electron can absorb this photon. That's how we describe forces in quantum field theory. And this way the electrons interact. That can change the electron's momentum. Each emission or absorption must obey conservation of momentum. If the photon moves in one direction, the electron must move into the other. So, that's how an electron can change its movement. If we picture this process frame by frame, we get a Feynman diagram. It's basically just describing a possible particle interaction within quantum field theory. But hold on, quantum field theory. We are talking about a quantum theory. We already had quantized energies, but apart from that, there's another pretty fundamental feature of quantum physics. You know that things can be in a superposition. The cat is dead and alive, or a particle is in multiple places at once. Well, within the path integral formulation of quantum field theory, particles take multiple paths at once. Actually, they take all possible paths, but paths that are more likely contribute more than others. So, if we look at two electrons, we not only get this interaction, but every possible interaction. If you have an electron and its antiparticle, a positron, they can also do this. That's how a field can destroy particles. The energy transfers to another field, and the other field then creates a particle. All of quantum physics, started with physicists studying the behavior of quantum things. And since then, the double-slit experiment has been a huge thing. But did you know that we usually teach about a wrong pattern? Check this out for more. Thanks for watching. Have a wonderful day.